Hi everyone, I'm Dr. Jared Boasen. I'm back with the next segment of our EEG tutorial video series. So now we've applied the conductive gel on all the electrodes on the EEG cap. We've re-verified that the cap is in the right position on the head. And I'd like to show you now the extent to which we can actually see things happening in the raw signal. Now remember that we do have some display filters applied right now, which is good because otherwise we wouldn't be able to see the things I'm about to show you. So the first thing I'd like to show you is the extent to which we can see physiological noise. So that means signal that's entering into the EEG recording, but it's not originating from the brain. It's coming from somewhere else in the body. And typically that can be from muscles. Muscles in your neck and shoulders are very common problems in EEG recordings as people sit for a long time or get tension. The other problem is clenching of teeth. These sorts of muscle flexations cause very strong electrical signals that can traverse all the way from their origins up into the scalp. So I'm going to ask Anne right now to please clench her teeth, and you'll see the amplitude change on the raw signal. And stop. Again. And stop. So you can see instantaneous change in the amplitude of the signal as Anne has this flexation in her jaw. So the jaw is relatively close to the scalp, so it's very easy to see this. But you can imagine in a study where a participant is needing to speak or they might be nervous. So it's always important to ask participants to remain relaxed. You should also minimize any sort of talking in a study to the extent that you're able to. If you're not able to eliminate talking from a study, for example, if it's important somehow for the experiment, that's okay. But you need to think about strategies to target time points in the recording where the participant isn't talking, if at all possible. The next thing I'd like to show you is what happens when the participant blinks. Blinks are another big source of artifact in the data, and usually one which we have to, and thankfully are able to, clean out in the post-processing. So Anne, I'd like you to blink hard 2 times. Good. You can see that it causes a big shift in the signal, and it's taking a while for it to recover. Please blink 2 times again. Good. You can see that particularly there's amplitude change on FP1 and FP2. That makes sense because these electrodes are actually the ones that are closest to Anne's eyes. Normally the blink artifacts will be the strongest there, and the amplitude will decrease as we move to the occipital electrodes in the back of the head. Perfect. Now the next thing I'd like to show you is that we can actually pick up changes in brain activity when we look at the raw signal. I'm going to do something here. It's very subtle, but we can pick up changes in the alpha band. The alpha band is one of the strongest neurophysiological signals that the brain has. It's around 8 to 13 hertz in frequency. And there's a known phenomenon that when we close our eyes, we will cause an increase in the amplitude of the alpha band. So I'm going to ask Anne to close her eyes in a relaxed way and keep them closed. Now open your eyes. And close your eyes. Keep them closed. This is harder to see because this is not physiological, this is neurophysiological. Open your eyes. But you should be able to notice, particularly around P7 to P010, that as Anne closed her eyes, the amplitude of that signal increased ever so slightly. One more time, please close your eyes. And open your eyes. And when she opens her eyes, you can see that the amplitude again drops back down. Once more, is particularly noticeable in P7 through the occipital electrodes. This matches with classic literature on the observation of the origins of alpha signal, which are typically seen in posterior and occipital electrode sites. Thank you very much, Anne. That was perfect.